The subject paper, a high-performance Delta-V thrust module for CubeSats and SmallSats, is presented by Cleve Sampson, Joe Cardin, and Chris Day of VACCO Industries. The design philosophy of the thrust modules is to make it a very simple system that can be produced in large quantities at low cost. For this reason, we selected a blowdown architecture because it eliminates the need for pressure control. Either electronic pressure control or mechanical pressure control are not required. The maximum design pressure resulting from this is only 400 psi, and the system uses a standard 28-volt input. The standardized manifold assembly contains all of the functional components and is common to every thrust module. Only the propellant tank, which is a simple titanium piece part, is customized for various applications, so that if a customer needs more or less Delta-V, or they have a restricted volume available, then the propellant tank can be customized with minimal cost impact. The propellant valves are suspended armature, high reliability valves. They're normally closed and have been proven in other applications. The 1 Newton thruster is mounted axially, therefore it's suitable for Delta-V only. 82 of these thrusters have been flown on 21 spacecraft, so the design is well established and has a very impressive heritage. The initial thrust is 1 Newton, and as the propellant is consumed in this blowdown arrangement, the final thrust at the end of life is 150 millinewtons. At all times when the user wants to fire the system, they know what thrust they're going to get because they can detect that with a pressure transducer that is directly proportional to the thrust level that will result when you fire the thruster. The thruster itself is qualified for a throughput adequate for more than 50,000 Newton seconds of total impulse. This is, of course, extreme, but does illustrate the capacity of the thruster. The minimum impulse bit is 50 millinewton seconds, which for an axial Delta-V thruster is very good. The thruster itself includes two 8-watt heaters, so the thruster has redundant catalyst bed heaters that are under the direct control of the user spacecraft. There's also redundant thermocouples that sense the temperature of the catalyst bed so that you can preheat it for 30 minutes. You can monitor that preheating and then fire the thruster. And by noting the temperature of the thermocouple, you can determine whether that thrust was in family or not. And that's a handy feature. The 3-seal mini fill and drain valve is a standard in-house VACCO design that's been produced many times before for many applications. The pressure transducer provides the fuel state. In other words, it's used purely as a fuel gauge, and it's not required to operate the system. The output of the pressure transducer tentatively selected is 0.1 volts to 4.9 volts. And that output voltage would be proportional to pressure, which is also inversely proportional to propellant remaining. The total error band of this pressure transducer is 1.5% of full scale. This results in a system that enjoys many safety features. The green non-toxic LMP103S monopropellant, of course, is the major one. It can be shipped anywhere in the world via commercial aircraft, and the system itself enjoys 3 seals against external leakage. Now that 3CO requirement is a hydrazine requirement. It's not strictly required for this green non-toxic system, but we built it in anyway in an abundance of caution and in order to be as rain safety friendly as possible. The electronics assembly is purely optional. It's not needed to operate the system and is a separate bolt-on subassembly should the customer elect to include it. This is the envelope of the system. As you can see, it's roughly cylindrical with the manifold assembly at one end and a hemispherical dome at the other. It consists of two major assemblies. The first, of course, is the armature or manifold assembly, and the other is a simple piece part that is the tank and with its mounting flanges. So when this system is customized, the relatively complex manifold assembly stays the same, and only the propellant tank piece part is customized for the application. There are going to be standard sizes of these tanks that would trigger no additional cost, but they can be customized or scaled per the customer's requirements. The manifold assembly consists of a machined manifold and that accommodates the pressure transducer, the three propellant valves, and the mini fill and drain valve. Mounted to the front face of this manifold assembly, of course, is the LMP103S thruster itself. And on the far side, you can see the electrical power and data connector that's provided for the convenience of our customers. The mounting flanges, being part of the propellant tank, can also be modified per the customer's requirements if necessary without affecting the manifold assembly. The blow-down nature of the system is the key to its simplicity. The propellant storage tank, you can see here, is this green circle. The helium ullage is built right into the same tank, so it's loaded right on top of the LMP103S in order to pressurize it. There's a 3CO mini fill and drain valve that's used to fill both the LMP103S and the helium. The pressure transducer is mounted directly to the tank so that any potential contamination from the installation of that pressure transducer or inherent in the pressure transducer would be filtered by the filter/PMD at the outlet of the tank and would not be able to contaminate the balance of the system. System is designed for flushing in one direction, never back flushing, which eliminates many of the opportunities for contamination to cause problems. There are three valves in series between the propellant tank outlet and the thruster itself, as mentioned earlier. They're arranged, of course, in series, and there's a test port included in the manifold in order to be able to sense the system or flush it or for test purposes. That's merely a convenience and is not strictly necessary. The thruster itself, of course, is mounted to the far right-hand side. The table shows some of the performance of the standard sizes, the 2000 cc through 3300 cc and 4200 cc tanks. These values are all with the 1 Newton thruster, all with the LMP propellant. Although the system is designed for a variety of other thrusters and propellants, it can be adapted very easily. These three sizes of propellant tank give rise to three different total impulses with that range from 3785 Newton seconds for the 2000 cc design up to 8259 Newton seconds for the 4200 cc system. Now these, of course, can be modified to be either more or less by modifying the propellant tank. As mentioned earlier, the ultimate limit is over 50,000 Newton seconds. The volume of the system or its envelope is shown here. Overall, it's about 6.5 inches in diameter. and about 12.5 inches long. However, only half of that occupies the spacecraft. The rest protrudes from the spacecraft, and that's ideal for access to the fill and drain valve, but also for exposing the LMP-103S thruster to the cooling of deep space. The thruster itself, of course, is the key component. The rest of the propulsion system exists to bring propellant to this thruster. It is an LMP-103S monopropellant thruster. That means that it's based on ADN as its basic propellant. That propellant is non-toxic, non-carcinogenic. It can be flown anywhere in the world on commercial aircraft. And when fueling, you don't need a escape suit. So fueling can be done much, much easier in a variety of different locations because of the lack of need for space escape suits. The impulse of a LMP thruster is 6% higher than hydrazine, and the higher density, the 24% higher density of LMP versus hydrazine means you can store more of it in the same volume. The storage can be left for up to 20 years, and in fact greater than 20 years, without the propellant being harmed or damaged in any way. It's insensitive to space radiation as well as air and humidity. And the broad temperature range of this propellant is an advantage over hydrazine as well. Since hydrazine is roughly the temperature range of water, the temperature range of LMP is -7 degrees C to plus 120 degrees C. So the thermal control requirements are less. The 1 Newton high performance green propellant thrusters are well established in terms of their qualification and their flight heritage. 82 of these thrusters have been flown very successfully. They've been flown for over 10 years, and they're qualified for 60,000 pulses and a maximum continuous firing of 1.5 hours, so 1.5 hours. The exhaust gases are non-corrosive, which is always an advantage. The thrusters themselves are thoroughly tested during acceptance testing at Bradford ECAFs before delivery to VACCO. This is a pattern that corresponds to other systems that, conventional systems that are stick-built. They all have their thrusters tested at the thruster level and then incorporated into the system and are fired for the first time on orbit. This slide illustrates the depth to which the hot fire ATP is conducted. The testing is very thorough, and the thrust of every particular thruster is thoroughly characterized through hot fire testing. The optional analog electronics assembly, or AEA, is just that. It's an option. The system can be provided, and the standard system is provided with no controller whatsoever. The customer directly controls the valves and reads the pressure transducer. In this case, the analog assembly is a collection of valve drivers that can be provided for the convenience of our customers, so that instead of directly applying 28 volts to the valves, you would be providing a logic level signal that will drive the valve. And the purpose and advantage of this assembly is that the valve drivers have a built-in drop-down current, which reduces the power consumption and allows you to keep the valves on indefinitely. But also the back EMF is blocked so that the controller or the customer's power system does not have to deal with the back EMF. In conclusion, VACCO has been designing and building small satellite propulsion systems since 2003. We've built 40 of these systems of 16 different designs. The experience gained and lessons learned have steadily improved the performance and reliability of these systems. VACCO designed a simple high-performance green monopropellant propulsion module that shortens lead times and lowers cost. The system is self-contained and provides delta V thrust. It has a green thruster, feed system, and propellant storage, and a bolt-on plug-in assembly. The host spacecraft controller directly controls the thrust module. The system provides 3 seals against overboard loss of propellant, and the propellant tank geometry can be customized for a total impulse as high as 50,000 Newton seconds. The pressure transducer is flight qualified and accurately measures the remaining propellant, so it acts as a fuel gauge. A flight qualified fill and drain valve provides the propellant and pressure and fluid interface. And an optional electronics assembly can be added that provides valve driver circuits that suppress back EMF and regulates voltage to minimize power consumption. The initial thrust modules use flight-proven LMP103S green thrusters. The thrust module has been designed, however, to be compatible with other green propellants and other thrust levels. So future systems will take advantage of that flexibility. Thank you very much, and this concludes our presentation.